Tel Aviv University. He works in several collaborations and several experiments in particle physics, in Atlas, Belle 2, also at Babar. He's an expert of display vectors or long-lived particle searches, several experiments, and he will talk today about the heavy neutral lepton searches at Atlas and Belle. Thank you, Avi, for your time, and please go ahead.
Thank you very much, and thank you so much for the introduction. Let me just say that if anybody feels like turning on their camera, please do so. It'll be nice to see that I'm talking to people, and if I say something stupid, maybe your face will tell me that I should change what I said. So as Juan Carlos said, I will talk about, I slightly focused a little bit more the title of the talk to talk about searches for heavy neutral leptons at Atlas and Belle. The picture I chose to be, let me tell you that usually when I give a talk somewhere, especially at a conference, I like to, on the first day, take some pictures of the place and then to use those for my title slide. And actually in 2016, as was mentioned, I was at Valparaiso, and let's see how, yeah, here. So I selected some slides from that wonderful visit to the beautiful city. But then I of course figured, you know these pictures better than me, these places, so probably I should stick with something from my home, which you'd be more interested in. So this is a flower and flowers from an apple tree in my yard, and the meaning of that will become clearer as we progress. So I will talk about, first I'll talk about long-lived particles as probes of new physics, and I'll mention these acronyms LLP for long-lived particles and NP for new physics. I'll then discuss the problem of neutrino masses and show how these come together in these long-lived heavy neutral leptons, which I'll call HNLs. And let me say that the introduction I planned was at the level of graduate students that are not specialists, so I might be going a little bit too slow for people who are more familiar with the topic. And so far, this will be theory. And I'll spend quite some time on that. And then I'll also spend quite some time on the search we recently completed at Atlas, the HNL search. And I'll say not too much, but something about the search that we're currently undertaking at Belle. And very briefly, then I'll just mention additional proposed searches at B factories for these long-lived particles in various other scenarios. So, of course, the question for everything in particle physics is we have the standard model Lagrangian, and what else? We had the hierarchy problem, which suggested that we should look at the LHC for new particles with this mass range. And that went together with what was called the WIMP miracle, which is if we have particles in this mass range, then one of those particles could be the dark matter particle, and everything just fits right. But that physics has not yet been found. And so sometimes it's good to find guidance in theory regarding where to look for experiments in physics, but that's not always the case. As we've seen in this case, the most naive expectations did not materialize. So people are actually now looking for, and have been for quite some time, for new particles, which are the indications of new physics in various new ways, and various ideas that initially seem weird, like this weird-looking lemon, again from my yard, then often become mainstream. And one area for which this has happened is long-lived particles. So let me give you a little bit of introduction to that. When one searches for new long-lived particles and for new physics, we can kind of just draw everything in terms of the interaction strength and the mass of the particle. So the known physics, the known particles have large enough interaction strengths that we can create them, and small enough masses that we, again, can create them in colliders. But if we go to higher masses, this is where we start exploring the energy frontier, which is what LHC mostly is doing, and in some cases, some other experiments. And if we go towards weaker interactions, that's the intensity frontier, which again, many experiments are exploring. And somewhere in this region of relatively low mass and relatively small interaction strengths, you have long-lived particles. And that's the area that I'm going to focus on here. And I'll show you that they provide an excellent way to probe new physics, again, in this region of parameter space. There's also another dimension to it, which is the creativity frontier, which I guess you can assign to any area of science in general. But I think we see it as particle physicists, we see it as, new ideas in both theory and experiment that people are coming forward with. And it's really fun actually to explore this additional dimension. And I'll give you a little bit of maybe hopefully a hint of that. So these long-lived particles are one such class of weird searches. It has seen a lot of growth in recent years, again, due to the availability of LHC data, the lack of LHC discoveries, and again, the creativity frontier, new theoretical and experimental ideas. And let me just point you to some resources on that if you're not familiar. There's a series of workshops that I think Giovanna has been involved in, at least some of them. And this is the category. I think now we're at the 12th workshop or the 11th or something like that. And as part of that effort, there is this very long document which summarizes long-lived particles specifically at the LHC. I, at that time, also wrote with the colleagues with whom I had done long-lived search analyses, another report which is a bit shorter and also looks at other non-LHC opportunities, but is less thorough probably than this one when it comes to the LHC. So all of these are resources with which to study the topic. And again, in the Indico pages here, you can find a lot of useful talks. And let me say what I mean by long-lived particles. So particles can be either detector prompt, which means that they decay too early to be for their flight distance to be seen. They can be detector stable, like muons and pions, which essentially are stable as they fly through the detector, or completely stable, like the electron. And the particles I'm interested in are these guys in the middle, which they are long-lived enough that we can see their, we call it their displaced vertex. We can see their flight distance, yet they're short-lived in the sense that we do see their decay. So these are what I'm going to call LLPs, long-lived particles. And again, the standard model has several examples of these particles. And there are various ways to have a long lifetime in general. So weak particles, weakly decaying particles are generally long-lived because they're much less massive than the W boson through which they decay. So if you have a virtual particle mass, that makes you long-lived. That makes a decaying particle long-lived. Another possibility is that you have some very small couplings. So for example, B mesons are long-lived because they decay via VCB, which is much less, I should have had here much less than 1, but it doesn't matter. So that's essentially what makes them long-lived in addition to this W mass suppression. And you can also have another possibility is to have small phase space, which is, for example, why the K long lifetime is much longer than that of the K short, why the neutron lifetime is much longer than that of the kaon, for example. And in new physics, particularly in supersymmetry, there are various examples that one can see exactly these effects. And I've chosen here two examples or two categories of examples from searches that I worked on. This one, the first one, I believe, is the one Giovanna was also involved in. So in this case, we have a long-lived gluino because the squark is very heavy. In this case, we have a long-lived neutralino because it decays through these very small R-parity violating couplings. And this is not a search that I worked on, but others have. But this is an example of a neutralino, which is chargino, which has almost the same mass as the neutralino, and that small phase space is what suppresses its decay and makes it long-lived. So there are examples like this in the standard model, and also one can think of those examples in new physics. In this case, again, I gave examples of supersymmetry. So now I want to leave the question of long-lived particles and talk about the problem of neutrino masses. When you talk about neutrino, you might think of this animal, which is called a newt, but it's spelled with a W. So nonetheless, it's a kind of a cute animal to as an opening to start talking about neutrino masses. So the standard model has only left-handed neutrinos and they're massless, but we know that neutrino oscillations takes place, neutrino flavor oscillations. And for me, this is a nice picture that shows that. It shows the results by the Super Kamiokande experiment, which is situated like over here in Japan. So they can see events which come from neutrinos produced in the atmosphere above them are only like 20, 30 kilometers above, whereas those that come from the other side of the Earth are travel a much longer distance, and they can see as a function essentially of the distance here that muon neutrinos, there's a muon neutrino deficit that increases with distance for a given energy. And the reason for that is that neutrinos oscillate from being muon neutrinos to being tau and electron neutrinos. And from a variety of experiments, we know the squared mass differences between these neutrino eigenstates, the mass eigenstates, and they're of order 10 to the minus 3, 10 to the minus 4 eV squared. And there's also an absolute limit on the neutrino mass at less than 1.1 eV. I think actually I maybe should have updated that. I think it's 0.9 now. But nonetheless, this is sort of the scale of what we know about neutrino masses. So they're at least 10 to the minus 1 or so, some of them, but 10 to the minus 2 EV for some of them, but others could be a little bit more heavier than that. Nonetheless, very light. So how do we generate neutrino masses? So here's the standard model, the fermions of the standard model. And for each fermion, we have 2 degrees of freedom, the left-handed and the right-handed, except for the neutrinos, where we have only the left-handed neutrinos and no right-handed neutrinos. And if you augment the standard model with these right-handed states, which I will call, or this model calls N1, N2, N3, this is what's called the new minimal, neutrino minimal standard model, just adding these guys. Then once you have that, then it's natural also to add a Dirac mass term, just like the other fermions have, to generate the neutrino masses. And that essentially solves the problem. However, with these masses being very small for the neutrinos, we see that we require this Dirac mass for the neutrinos to be about 10 to the minus 6 times smaller than the electron mass. Naively, this is not so strange. This is about the ratio between the electron and the top mass, but we do see that for all the neutrinos. So it calls for the question of whether there's a general mechanism that suppresses all the masses of the 3 neutrinos. And such a mechanism is called the seesaw mechanism, where we also add a Majorana mass term, which looks like this. Here, the C superscript means that it's the CP conjugate of the fermion field. So what these terms do is they turn a fermion into an antifermion, a neutrino into an antineutrino. This is something that you never see for any fermions because all the other fermions have conserved charges. But in this case, we're doing that just for the right-handed neutrinos, and the right-handed neutrinos are not charged under anything. So it's no problem to turn a right-handed neutrino into its antineutrino. They're the same state. They are, we look at them as, or they should be Majorana fermions. And so we can allow for this term as well. So then adding the 2 mass terms together, we have a mass matrix like this, which we can then diagonalize to find the mass eigenstates. So let me clarify, this neutrino left and the neutrino right are the eigenstates of the left and right projection operators. But if you diagonalize this matrix, you get linear combinations of these, which are a mass eigenstate. So these are what we call physical particles. They have a definite mass and definite lifetime. So essentially, the propagation in time is what measures them, that measures their properties. So in the seesaw mechanism, if you then diagonalize the matrix, you find these 2 mass eigenstates. The light neutrinos have a mass which is the Dirac mass squared divided by the Majorana mass, which appeared in the Majorana term. And the other linear combination, which I'll call N, or the HNL, the heavy neutral lepton, has approximately the Majorana mass. And so this is called the seesaw mechanism because if you make the Majorana mass heavy, you make you make one of them heavy, you make the other one light. And that explains why the neutrinos that we see are have a low mass. So these are the neutrinos that we already know, and this is the extent of what we know about their masses. And there's also the HNLs, which we then want to go out and find experimentally. So you can ask, what is the mass of the HNL? What is this Majorana mass? So of course, that depends on what you assume for the Dirac mass, and given what we already know about the light neutrino masses. So if you assume that the Dirac mass is, say, a GeV, which is, like the other standard model you cover, like the strange, the charm, the bottom mass, then you find that the Majorana mass is very large. It's 10 to the 6, 10 to the 8 GeV. So, it's not very relevant for LHC. But if you make another assumption, which is that the Majorana mass is of order GeV, so you have the HNLs that you can find in colliders, that means that the Dirac mass is 10 to the minus 3, 10 to the minus 4 GeV. This is of order what we know of the electron, so it's not so strange, even though you can argue that it doesn't naturally explain why the neutrino masses are so small. Nonetheless, the fact that it doesn't seem natural doesn't mean that it's wrong. And there are several advantages to this mass range. So, for example, you not only can explain the light neutrino masses, but you can also have a dark matter particle. So the lightest HNL could have a mass of order KeV and is stable on the scale of the lifetime of the universe. And also the matter-antimatter symmetry of the universe can be explained via leptogenesis. This is not necessarily just a property of the seesaw mechanism. So for me as an experimentalist, HNL masses of order GeV or maybe 10 GeV just present very nice opportunities for interesting studies. So that's why I'm focusing on them. And if they're there, that's great. I'll see you in Stockholm. If not, then at least we have ruled out a region of parameter space, which has so far been what we've been doing at LHC. So to summarize, the light neutrino is a linear combination, which is mostly the left-handed neutrino and has a little bit component, which is the right-handed neutrino. And the HNL is mostly the right-handed neutrino and has a little bit of a component, which is the left-handed neutrino. And because of this component, it can undergo standard model interaction, just like the left-handed neutrino, except with an extra suppression by this factor V, where I've assumed that V is much less than 1. So for example, the HNL can be produced in Z decays. So essentially the Z would go to a standard model neutrino, a left-handed neutrino plus the HNL, and I've broken this down to, it actually goes to the left-handed neutrino, which mixes with mixing strength V with the HNL, similar to what we do for the CKM matrix. And you can also produce them in off-shell decays of mesons, in the case of mesons, which essentially mean via off-shell W. In that case, you have a lepton and an HNL, or you can also make them in lepton decays, and I'll show that later. So you have a lepton that decays to the HNL plus a virtual W, which would go to whatever W's go to. So now let's talk about the HNL decay. So again, it would decay exactly by the same vertices. It has this vertex just like the standard model neutrino and the other vertex for the W star. So this is the HNL decay via a charge current and neutral current. So it can go into it can go into a neutrino and 2 leptons, or a lepton and 2 quarks, or in this case, via neutral current decay would go into a neutrino and 2 leptons, or a neutrino and two quarks. Okay, it can also, of course, go into the 3 neutrino final state, which would be a little bit unfortunate. Okay, and it turns out that if you write the width of the HNL, it of course looks just like the width of a standard model fermion, except suppressed by this factor V squared. And if you turn that into C tau, it's of order a millimeter times 1 over the V squared, which again can be a small number, which would increase the lifetime, and 1 over the HNL mass to the 5th, roughly, in in units of GeV. And I've ignored some phase space here, and that's why the approximate here. So there's a very strong dependence on the mass, just like it is for standard model fermions. And so as the mass changes, the lifetime changes very rapidly for the same value of the mixing parameter. So far we've been discussing theory. Theory has nice flowers and promises to bear nice fruits later, but we haven't seen the fruits yet. Yeah, this is just theory. So the next thing we need after theory is we got to have data. So data is when your fruit are on the tree. So actually this year we got a very large harvest of these apples. We get like, I think, a few kilograms every day, and mostly they fall on the ground and we just collect them off the ground. The problem, as I think you can see here, is that not only we like the apples, but also the worms like the apples. So inside they have some not very nice regions that we have to clean and cut out. And that's, real life particle physics data is like that also. You have background and you have bad events and things like that that you need to clean out. So I guess our apples are kind of like that in that sense. Nonetheless, after we do that, we get to enjoy them. So let me show you more of that. So various experiments have looked for HNLs and have set various bounds on them. So far, this has only been done always with mixing with respect to one flavor. So the assumption is really that usually that there's one HNL that the experiment is looking for, and it mixes in this case only with the electron neutrino, or with the mu neutrino, or with the tau neutrino. And some of these searches are for prompt decays, like this one, for example. So the HNL is short-lived, which is what happens at high mass. And some of them are for long-lived HNLs. And let's look at this projected limit from FCCEE. I should say the filled regions are published searches with limits, and the unfilled ones are projected, proposed things that could be done in the future. So let's look at this search, for example, proposed search, because it shows very nicely the features of a long-lived search. So generally, the region which is excluded looks something like this. It can be closed depending on how they do it. And what happens here in this region is that the coupling is too small and the HNL is too light, so that too many of the decays occur outside the detector. And so if you're looking for a displaced vertex, you're looking for the decay of the HNL to one of the final states that I showed inside the detector, you're just not going to see enough of them in this region because, again, they decay outside the detector. The opposite region is this one. And here what happens is that the decay tends to be too short-lived. Yeah, so it looks like prompt, it looks like background. And very often what happens in this end here is that you also run out of phase space to produce them. You don't have high enough energy, etc. So this is the characteristic shape of these long-lived searches. And you can see, very large regions have already been covered and other regions have not been. This is a summary from a paper in 2015, so it doesn't include a couple of recent searches that I'd like to show. So this actually is a search that I participated in. We have in the same plot a long-lived search and a prompt search. So the long-lived search shows this teardrop shape that I mentioned. And this was done only with part of run 2 LHC data. So we used only about 23 inverse femtobarn. And the prompt search doesn't suffer from this problem that it's only sensitive in a very small mass region. Yes, as the mass changes by a factor of 2, the lifetime changes by a factor of 2 to the 5, and so the long-lived searches are only sensitive in a small region. The prompt search is sensitive in a much wider region. However, in this region, it is much less sensitive. Okay, and the reason for that is that the long-lived signature is very effective at suppressing background. And so as a result, over here, we have a very sensitive search, and the prompt search is not doing as well. A much more recent search is that of CMS. Now, by now, they use the full run 2 data. and they made several improvements. So their search is more sensitive than what we published in 2019. Ours was the first from LHC of this kind, and by now they have a more up-to-date search. And the search that I'm going to show you now is more similar to this recent CMS search. So our search is done with the Atlas detector. I won't go through the whole explanation of the detector, just to say that everything we're looking at is really inside the first 30 centimeters of Atlas. And we use the calorimeter and the muon spectrometer only really to identify electrons and muons. And I'll show a zoom in of that inner part of the detector a little bit later. What we do in our search, which was submitted to PRD, and this is the archive number, is we look at on-shell W production, and the W then decays to a prompt lepton and the HNL, which is long-lived, and we look for the HNL decaying into 2 additional leptons. And so our signature is this prompt lepton and a displaced vertex, DV, displaced vertex, which can be either EE, mu, or EMU. We use the full run-to data of 139 inverse femtobarn at 13 TeV. The cross-section for W production is about 200 nanobarns. And so the branching fraction for the W to create this lepton and HNL is essentially the same as the standard model, branching fraction times V squared. So that if you run the numbers, that gives us 20 million times V squared. Okay, so that's the number of events we expect. And this kind of gives you an idea of the sensitivity of V squared that we expect to have. So something of order 10 to the minus 6, essentially. So let's see how we do the analysis. So note that the HNL daughters are displaced. So if this is the interaction point, and maybe the HNL decay took place over here, the 2 daughters, I'm sorry, I drew them with the same charge. I shouldn't have done that. One should be going the other way. It's interesting how many talks I've given, and only now I noticed that. And nonetheless, if the HNL decays here, the 2 tracks that it produces, the 2 leptons, have a large impact parameter, a large D0 with respect to the interaction point. And we can only track, or the Atlas the default tracking, which is used in the trigger, can only track tracks which have a D0 of which is less than 10 millimeters. And so that means that these tracks may not be available for the trigger. So what we use is we only trigger on the prompt lepton. We require it, the requirement depended on the run, but then we kind of clean up that requirement by requiring that the prompt lepton has a PT of 28 GeV, which is not so low given the W mass. Now let's focus on how we reconstruct the displaced vertex. So the Atlas inner detector has 4 layers of pixels, and then starting at a radius of 300 millimeters, 4 layers of silicon strip detectors. Beyond that, we have about half a meter of drift tubes, which only give X and Y coordinates. So they don't give a 3D coordinates with which we can find 3D tracks and find a 3D vertex. And so we really need the tracks to leave hits in the SCT, in the silicon strip detectors, in order to find the vertex. And that's why we essentially have an outer limit of the fiducial volume of about 300 millimeters. So we actually require the vertex to be at no greater a distance than 300 millimeters. There's also a limit at 4 millimeters, just to remove prompt background, and that limit kind of goes back to our very first displaced analysis, which I showed you earlier. We also require, which is kind of natural, that the tracks that originate from the displaced vertex don't have any hits before the vertex, so at an more inner radius, because then that means that they're prompt tracks. Then offline, we still want to reconstruct these tracks which have a large D0. So what we do is we do what's called a large radius tracking, where we remove the hits that are already used and use the remaining hits to track additional, to find additional tracks with a large impact parameter. And that greatly increases the efficiency for large displacements of the long-lived particle. Now, for the first time, something which is done in this analysis is to calculate the HNL mass. Now, The HNL decays to a neutrino and 2 leptons. So naively, you would think that we cannot reconstruct the mass because we cannot reconstruct the neutrino. And if you count the number of unknowns, you would realize that you have 12 parameters of the decay that you don't know. Those are the 4 momenta of the neutrino, the HNL, and the W. However, there are also 12 constraints. So 8 constraints come from 4 momentum conservation in the W and the neutralino decays, And 2 constraints come from the fact that we know the W and the neutrino mass. Well, we know the W approximately, that's fine. And the neutrino mass we can take to be 0. And we have 2 additional constraints from the position of the displaced vertex that gives us the flight direction of the HNL. So if you count, that's again 12 constraints. You can write analytic equations and you can solve them. At some place, there is a quadratic equation because a mass always involves a quadratic equation. So there are 2 solutions, but it turns out that it's enough to use one of the solution, the one with a plus in front of the square root. And you can see that in terms of this calculation, here's Monte Carlo with 5G VHNL, and here's Monte Carlo with a 10G VHNL and with a 15G VHNL, and you can kind of see that we have not a great resolution, but we can kind of reconstruct these particles. So what we do is we use this MHNL. We have very little events actually. So the mass of the HNL, this MHNL, is used really only in 2 bins. There's a signal region, SR, which is up to 20 GeV, and a control region, which is between 20 and 50 GeV. And the reason for using this as a control region is that in this scenario, an HNL that would have this mass would be long-lived, would decay promptly, and so it would be removed by the 4 millimeter cut, and we wouldn't see it anyway. So we use this for the background, for our background estimate. And what you see here is that in the data in this particular channel, where the prompt lepton is a muon and the displaced leptons are a muon and an electron, we have this is 2 events in the signal region, and we have these events in the control region. And you also see the background estimate given by this purple histogram, and I'll explain later how that's obtained. So we normalize the background to the events in the control region, and that gives us our background estimate in the signal region. And then we say, how many events do we actually see? And that is the result of our analysis. So let me talk about the backgrounds a little bit. So these are minor backgrounds that we have cuts that reject. So there could be muons from cosmic rays. There could be decays of bees and charm particles. There could be particle interaction in the detector material. And there could also be Z2 lepton-lepton decays where one of the leptons is the prompt lepton, and for some reason we miss hits on the other one, and it becomes the second, the displaced lepton. So we have cuts to very effectively remove all of these backgrounds. The remaining background, which is the dominant background, is accidental crossing of leptons. So at every collision at LHC, you have something like on average 50 interactions. They produce a lot of particles. Some of those can be leptons. Some of them can be leptons produced in hadron decays in flight. Some of those could be hadrons which are just misidentified as leptons. So there are various things that could happen to them. And in addition, any 2 of those particles might just accidentally meet in space, and that would look like a displaced vertex. Yeah. So and we actually verified that this is the dominant background by looking at the same sign and opposite sign vertices, which are supposed to be populated roughly equally by this type of background, but that's not the case for the other types of background. And we see here indeed a comparison of the DV mass for same sign and opposite sign vertices is in good agreement. So to estimate this background, what we do is the following. If you assume that the 2 leptons in the DV are really unrelated because they come from accidental crossing, then they're also unrelated to the prompt lepton. So what we can do is we can take prompt leptons from one event and a displaced vertex from another event, and we can shuffle all of them together. We can combine all of them together, and that gives us about a factor of 10 to the 2 to 10 to the 3 more fake events than we have in the actual event. So each fake event has a lepton from one event and a displaced vertex from another event. And we can study them. We can calculate the HNL mass with these fake events. And we can compare it to what we see in the data. So if I go back 3 slides, you see that the purple plot here predicts a rather flat distribution for the MHNL in the control region. And this is an agreement with the events that we indeed see in the control region. And it predicts a certain complicated shape in the signal region, but this is due to the cuts that we apply, so we understand that. And the point is that normalizing the MHNL shape from these shuffled events, these fake events in the control region, allows us to estimate the background in the signal region. So this is probably the most important part of the analysis, is this background estimate. Okay, so that brings us to the results. We have cleaned all the worms from the apples. Well, they're not real worms, just the dirty things that the somewhat rotten areas of the oranges that they make. And this is actually, I guess, apple pie that my wife made from that. So let me show you the results, the unblinded results. So here are the different channels that we look at. And in some cases, we look at these are channels that specifically target Dirac neutrinos, whereas in this case, we can be either Dirac or Majorana. These are the background estimates in the signal region, and these are the number of events we actually observe in the signal region. So they're always consistent with each other. And these show the number of observed events in the control region and the background estimate, which is obtained by fitting everything together. So everything is in agreement, and we don't have an excess signal. We see the signal that we expect. So we proceed to calculate limits on the model. So we make various limits under the assumption that the HNL is a Dirac particle and Majorana particle. We look at mixing only with the electron neutrino or with the muon neutrino, or for selected values of the ratios between the various mixings, which are motivated by neutrino mixing experiments. And so here is one example of these results. This is for the Majorana with this kind of scenario in the inverted mass hierarchy scenario for neutrino masses. And this is what we get in that case. And again, these are some additional cases for given by the legend here. So this is the 2 quasi-degenerate HNLs in the normal hierarchy, for example. And this is the one HNL with single flavor HNL, which mixes only with the electron neutrino, for example. Okay, let's look at our results in perspective. So this is some of our results, and this is a comparison with the recent CMS results. So generally, they're very similar. Perhaps they go down a little bit lower than us over here. Maybe not. It depends on the scenario. And they go to, like in this case, to something like 15 GeV, and this is very similar to this curve in our case. They do go up higher in this region, and that's because they have a more clever suppression of prompt backgrounds, particularly a background from bottom and charm decays, whereas we did a more sloppy job, which is fine because this region has already been ruled by other experiments, in particular the Delphi limit, which is shown here. So we didn't do a very careful job at that, but we might next time. And you can also see what we have relative to the previous limits for, in this case, for example. So we exclude regions of, say, between, say, 2 GeV to, say, 15 GeV. So, like, kind of this region is what we exclude down to almost 10 to the minus 7. So maybe down to there. Okay. So that's where we are now. Of course, the future FCCEE, if it is indeed built, will and indeed has 10 to the 12 Z's, as is assumed in this curve, I think, then we'll do an even better job than us. So what's next for this analysis? So we're not done yet. We're actually expanding the search to use additional final states. So in particular, not just leptonic decays of the HNL, but semi-leptonic with hadrons. And we will also have a greater mass range, going down to both lower and upper masses with the full run 2 data, and also then preparing to use some of the run 3 data which is starting soon, which will be accumulated soon, in order to improve this measurement. And we're also looking at interpreting our results in a wider range of model parameters space, in particular in left-right symmetric models, which are very interesting in this case. Another question that you can ask is, what about an HNL, which preferentially mixes with a tau neutrino? And what happens if its mass is low? So as you saw, we only go down to, in Atlas, to, just a little bit above 2 GeV. CMS is similar. And for this HNL, the one that mixes with the tau, in this mass range, there's only the Delphi limit of, around the GeV. And there's some charm and nomad limits down to maybe 300 MeV, okay? And you can ask, why is that? And why can LHC not go to lower masses? So the issue is that the lifetime changes very rapidly with the mass. And in addition, at LHC, the boost is high. And so that means that low HNL has a large mass and high boost. And so most of them decay outside the detector. And so LHC loses sensitivity in this region. In addition, as I've shown you, the practical radius for Atlas at least is 300 millimeter. And furthermore, another killer is that it's very difficult to trigger on the soft tau, which would be produced in this case. So all of that really reduces the acceptance and the efficiency dramatically for LHC. However, you can study these HNLs in tau decays, and the best place to do tau physics is a B factory. I happen to be a member of the Belle 2 experiment also, and the Babar experiment. And so what these are E plus and minus colliders at 10.6 GeV. They have very clean topology for tau events without anything else. The cross section is almost a nanobarn. And so Babar and Belle together, which have about 1.5 inverse attobarn between them, have almost 3 billion taus already. And Belle 2 will have a 50 inverse attobarn. Furthermore, the boost is small. It's only about a factor of 3. And the practical radius for detecting them is larger than even at Atlas. And so as a result, this is a much better detector to study the tau mixing HNL at a low mass. And in 2019, we published this paper. And I see Juan Carlos is here of the authors. I guess the others are not. And where we suggested to do exactly that measurement. So the idea is the following: the tau decays to via a virtual W to a leptonic or hadronic final state, and an HNL. The HNL is long-lived. It can only undergo the neutral current decay, which can be to 2 leptons and a neutrino, or a neutrino and 2 quarks. And we only looked at the case where the decay is hadronic, and we mostly explored the case of a leptonic HNL decay. And again, in this case, despite the neutrino, you have pretty much the same 12 constraints as I showed last time. In fact, this was the first paper where these constraints were published. And we showed how to reconstruct the HNL mass and the tau energy, and to use those for background suppression. So our expectation was, given the Delphi limit in this region, that Belle and Babar could mostly do better for most of the parameter space, but Belle 2, which will have 15% femtobarn by say 2030 or 2032, something like that, could do better by almost 2 orders of magnitude. That was the expectation. Since then, we have started to actually do the analysis at Belle. So I'm doing that with my student Ori and postdocs Minakshi and Sorav. And it turns out that Belle has a lower efficiency than Belle 2. That's kind of not nice. Nonetheless, we have the data, and the analysis is essentially done and is currently under review. Let me just, because it's still not public, let me just show you a few ideas about it. So this is, again, data on the tree. These are not apples, these are pomegranates, which we also have. This is the state we will get to when we actually publish them. So we'll have the pomegranates at hand and we can eat them. So we have the K short which is a long-lived particle, which constitutes background. And so we have to exclude that region. Below that regions is where light HNLs pop up, like this one. This is Monte Carlo for 300 MeV. And above that region is where the heavier HNLs are seen. So we have these two different signal regions. We expect 0.8 events in the low signal region and 0.4 event in the high signal region. These are kind of arbitrary choices. It's very easy to tighten the cuts and to go to 0, but then you don't have anything to work with. And we have a data-driven background estimate with a control region, which is done similarly to the way the Atlas fit was done, where the HNL decays, not the HNL decays, but one of the muons is a pion. And we have various validation regions to check that our background estimate is working. And I can tell you that everything is working. So we hope to publish this very soon. Now, the original title of my talk was about long-lived particles in general. So before I leave, let me just leave you with this slide, that it's not just long-lived HNLs that are of interest, particularly at the B factories. So I think for Atlas and CMS, there's a lot of phenomenological work, but not so many people have looked at new physics at B factories, and there's a lot to be done there, it turns out. So actually, I myself have been involved in a suggestion for a heavy QCD axion search and an axion-like particle. Both of these are long-lived and can be found at B factories. With Claudio and Juan Carlos, we are and Nicolas, we're also looking at light neutralinos. Or we published a suggestion for looking at light neutralinos with R parity violation, and we're currently working on another idea on that together with Valerie, who I see is also here as well. So I think there's a lot of interesting things to do, and in the coming years, these proposals will turn into searches, which will make things even more interesting. Okay, so let me summarize. So as I showed you, the displaced vertex signature provides very strong background suppression. So this results in very sensitive searches for new physics when the particles are long-lived. These GeV scale HNLs can explain neutrino oscillations. It turns out they can also solve the dark matter and baryon asymmetry problems of the standard model. This is one example of our recent Atlas search, and again, CMS has a similar search covering roughly this mass range, and we are right now expanding to additional parameter spaces and additional final states. For low mass HNLs with direct coupling to the tau, the B factories are the best place to do this search, and again, this is one result that we predicted, and we're actually now working on the actual measurement. And there are additional ideas for long-lived particles searches at B factories, of course, at LHC as well. So let me just say thank you, and I'll leave you nonetheless with a picture from Valparaiso. Thank you very much.
Thank you very much, Avi, for your very nice and interesting talk. Is there any question?
I have a question.
Please go ahead.
Thanks, Avi, for the talk. I really like your fruit analogies. I'm also growing lemons in my balcony.
It's just that what I do most of these days is to cut apples, so it's really occupying.
No, it's great analogy. Thanks. So perhaps this is something that you will do for run 2 for the Atlas HNL search. And I was wondering the reason why you are not, or you did not look at multi-track displaced vertices. I mean, you are actually reconstructing the leptons in the final state, and that will give you a better handle on the mass. You could fully reconstruct the visible decay products from hadronic W decays. So why is it that you focus on displaced dilepton vertices and not multi-track based vertices, which is something that we actually proposed in 2018 with Juan Carlos and Martin, and I haven't seen this analysis yet. So
we're doing that now. That's what we're starting. That's the analysis that is really just starting now. However, you know, there was the feeling that working with leptons initially would just be easier, and that in one final state we would cover both the charge current and the neutral current final states. And it really depends on the mass. You know, if you're looking at more in the 2 GeV range, the predictions for the hadronic final state are a little bit more difficult to make. Not the end of the world, but yeah, I agree. It's just a matter of let's do one thing first, and then do the second one later, and how much time we have, and when students need to graduate, and things like that. But we are doing that now. Regarding measuring the mass of the final state, that of course is true that in the hadronic final state you can fully measure it, everything, except then, you know, you do have the neutral current decays, which you then need to treat a little bit separately. So there's a little bit of a complication. An additional complication, an experimental complication, is that there will always be also pi zeros and neutrals. And so it's not exactly true that you can fully reconstruct the mass. Okay, I would guess that, if I had to guess, I would guess that in the semi-leptonic final state, if you reconstructed the mass of, say, a 5 GeV HNL, probably the resolution would be 1 to 2 GeV, which is not very different from what you have here. Surprisingly, maybe better. It should be better, but you know, maybe not that much better. Yeah. So, but you can gain also in branching ratio, right? That's true. From the big, that's right. Yeah. So there is a definite gain in branching fractions. That's right. So that's why we're actually now doing that. But as you know, from the very first displaced vertex search that we did, yeah, we said, oh, let's just start with the very simplest thing, and then we can do something more complicated. So this was kind of the approach. And we already expanded here relative to the previous search that I showed you. The previous one used only, used less electrons. So, and in this case, we used also a prompt electron. So. Okay, but I mean, it's more related to limitations in person power and not some physics limitation. That's right. Okay. Yeah, absolutely, yeah. Yeah. Okay, that's good. And I also would like to ask another question concerning the difference, the actual difference between Dirac and Majorana HNLs. So for the Dirac case, basically you are separating the sign of the final, the charge assignments of the final state leptons in these two different categories, lepton number conserving, and like same sign, opposite sign, but you also do consider the difference in this factor of 2 in the total decay width, right? Yes, right, yes. So how that translates into the mass reach for the two different cases? Does it change a little bit? So it really depends. So first of all, these two channels are when the HNL mixes only with the electron and only with the muon, right? So in this case, you can say that you actually had a E plus C minus, mu plus mu minus, and so it corresponds, to this final state. When that is not the case, so for example, in this channel, yeah, or in this channel, then the Dirac versus Majorana comes in the factor of 2 essentially, right? Otherwise, because you don't have direct access to that final state, but the limits are calculated using all the different factors. So, for example, this is the Dirac limits in these scenarios, and these are the Majorana limits in these scenarios. And I think if you make a one-to-one comparison, it's a little bit complicated, and I chopped the x-axis here, but yeah, that's all I can say. It's the factor of 2 in the lifetime is taken into account in the Dirac case. Okay, but perhaps the difference is, cross sections are the same. Everything looks. You just separate this in categories. You separate this in categories. Okay, it's just hard to see. I just need to look at the HEP data and to get the curves. Yeah, you can do that. So, for example, if you maybe choose this case, it's easier, right? So you can compare this green dashed to this green dashed, but it depends. I think the problem is that it depends on, it would be coming from the yield that we see here, but also the yields in the other cases like this one, and yeah. So yeah, so it would be this and this that would contribute to that. So it gets a little bit complicated.
Okay.
And the Majorana, so in the Majorana case, the rate that these contribute with a different weight, right? So it's not completely obvious.
Okay, I see. Thanks.
And of course gets more complicated in the two quasi-degenerate Higgs scenarios.
No, yeah, I'm just thinking on the minimal model first.
Yeah.
Thanks.
And yeah, right.
Okay. More questions? Please raise your hand if you have a question. Okay, I have one. Maybe it's a very naive question, but in this same search with the tri-lepton displaced vertex, can you go to the diagram, please, just to
like this
that
diagram?
one, yeah. Yeah, maybe you already answered my question, but in the case that the HNL prefer to mix with the tau, I was wondering if this search can be also sensitive to that, or obviously will be less.
Yeah, so we determined that actually the sensitivity was low enough that we determined that we are not even going to bother about it. So what happens here is this: if this lepton is a tau, and so the tau would have something like maybe 40 GeV total, maybe PT on average, let's say 30 GeV, and then decays to a lepton into neutrinos. So the lepton would have something like 12 GeV on average, and the fraction of those that would pass the 28 GeV cut is very small.
Okay.
And then again, you are hit by the tau leptonic branching fractions here. And so everything just becomes more problematic. It's not that it cannot be done, it can be done, except that it's not competitive with the Delphi limit.
Okay,
and
but
that's why it's not really worth the effort.
In the decay, what could avoid that problem using the decay mode through the C boson, right? So in principle, this same search should be sensitive to the product because of the mixing with the tau and the electron mixing with the tau and the muon, right? Because in principle, you can have this decay of N through the C boson, so the N decaying to tau neutrino and 2 electrons, for instance, or 2 muons.
Yeah, so it requires first of all, a more sophisticated trigger strategy that maybe picks up a lepton in level 1 or a jet and a tau jet, and then looks for a displaced vertex. And such triggers are now being written, starting to become available, but they were not available at the time. And it's not clear how efficient they would be. But in any case, we know that the efficiency would be small enough that being competitive relative to the Delphi limit is going to be problematic. So in the CMS limit here, we have the Delphi limit, which is probably applicable also to the tau. And so it's just difficult to be competitive with that given the current technology. Probably we can kind of reach that right now. But the question is, but you have to do a lot of work in order to reach that. So the idea is to wait to collect more data and to develop more sophisticated triggers, which is something I'm very interested in to, maybe do better by an order of magnitude with run 3 data.
Okay, great, thanks. So is there any other question?
Yeah, I have a naive question also about the Belle search. I mean, this is an ongoing search that you're actually doing with data? I mean, this is something that I didn't understand.
I mean, again, it's essentially done other than little things, but it's currently under review.
And this is, so you're producing the HNL from tau decays, you mentioned.
Right, yeah.
Okay, so is there any complication on the additional displacement that the tau can give you?
We treat the tau essentially as prompt. I mean, the displacement of the tau is of order of a couple of 100 microns. So it's not a big impact, 200-300 microns.
Okay.
Whereas for the HNL, we're talking about displacements of at least many centimeters or tens of centimeters.
Right. But you're not reconstructing the tau anyways. You're just looking at the.
That's right. Yeah, in applying the constraint of the flight direction of the HNL, we essentially compare to the beam spot, which if distances of 20 centimeters over versus 200 microns is we
sure
select the 200 microns.
I see. No, presumably I would have imagined that you will have some efficiency loss.
But due to the tau displacement, no.
Due to the tau displacement, yeah.
No, there's no issue with it.
Like in the same way, like you have HNL decaying to B's, for example, and the B's are displaced, so then you lose efficiency. Yeah, but
so
it
depends. Yeah. When the B's are a little bit displaced, the two B's might not make a single vertex, but in principle, you can, one can, work to take that into account in the case of the two B's. But in this case, it really is. That doesn't make much difference. Also, you're talking about bees that are quite highly boosted and maybe fly a few millimeters, whereas the tau in this case is only flying 200-300 microns.
Right, but a high energy tau can also no, it will never give you something of the order of millimeters. Is this what you're saying? Right. Or it also depends on energy.
I mean, the tau, the gamma beta of the tau is about 3.2, something like that. The C tau is 90 microns, I believe. Yes. So the average flight distance is 300 microns. Yeah. So maybe a millimeter happens, but it's not not a big deal. Because we don't try to. We only check that the pion is the prompt pion is consistent with the beam spot at like half a centimeter or something like that. I forget exactly this pion. So it's a very, very loose cut. Yeah.
Okay. Yeah. Maybe it's overly complicating things in my head. Thanks.
No, it's good to do that before you actually work on the data.
Okay. If there is no more question, thank you, Abby, again for this very nice talk. And thanks everyone. Thank you.